Lecture 5c on friction. Friction is a pushing or pulling caused by surface irregularities when two surfaces slide or try to over one another, such as the shoe on the surface. Macroscopically, the molecules from the bottom of the shoe interact with the surface. The molecular interactions can create bonds. The molecules, the rough surfaces, microscopically the atoms and molecules can dig into each other. Even smooth surfaces, such as things like glass and paper, when you microscopically look into them, they are quite rough compared to what we see macroscopically. It's these irregularities, the digging in of these irregularities, that creates the pushing or pulling between surfaces, that creates the friction. Thus, friction is a force. We represent it as subscript, as f, lowercase f subscript k, or lowercase f subscript s, for friction kinetic, sliding friction, motion friction, and friction static, friction when it's at a rest. The sled is rubbing on the surface as it's sliding, thus it's a kinetic friction. The frog is at rest on the incline, thus it's a static friction. It's the static friction that keeps the frog from sliding and having kinetic friction. But it's a surface on the sled and the surface on the frog. It's two objects in contact with each other, the surface on frog and surface on sled. It's just like any other force, but a force where the surfaces are pushing on each other in a parallel direction. Here we see a person pushing on a large object. This large box is being pushed, but the box is not moving. It's static. It's at rest. Her push is balanced by the static friction. We see on A, B, and C, she pushes more on the large box. The static friction responds. The more she pushes, the more static friction opposes to keep the box at rest. But eventually, her push overcomes the static friction. She can get the surfaces to slide. Her push overcomes the molecular interactions, the surface irregularities, perhaps even by breaking them. So her push is overcoming the maximum static friction. The equation on the bottom, the maximum static friction, lowercase f subscript s for static friction, maximum, is equal to mu subscript s. Mu is the coefficient of static friction. The coefficient of static friction, mu subscript s, is a measure of the surfaces interacting with each other. Greater values of mu subscript s means the surfaces rub into each other more irregularities between the surfaces to interact. Lower values of mu s, less interaction between surfaces. N is the normal force. The surface's response perpendicular in the normal direction. The surfaces pushing perpendicular to each other. N tells you how much the surfaces are dug in or digging into each other, governed by their weight. And mu s, how rough they are with each other. That's that they combine for the product of overall the force of friction. If she keeps pushing to overcome this static friction, eventually the object starts sliding. And you have kinetic friction. Kinetic friction is opposite the direction of her motion. Kinetic friction is serving as the sliding friction, trying to slow down or pushing of the crate. The kinetic friction is related by mu subscript k. Again, the surface is interacting, the coefficient of kinetic friction. But the coefficient of kinetic friction is less than the coefficient of static friction. It's harder to have friction when objects are sliding. It's harder to have interactions when the surfaces are sliding than when they're settled into each other. Answer this question on Blackboard about the coefficient of static friction, mu subscript s. Looking at a table of data between mu subscript s, the coefficient of static friction, the coefficient of kinetic friction, and the coefficient of rolling friction, we see there's a significant difference from static to kinetic to rolling. Kinetic is always less than static, and rolling is far less. Rolling is like an object, part of the object touches, such as a wheel, touches the ground, and then gets lifted up, and the next part comes down to press in, and then it gets lifted up as the wheel rolls for the next part to come in. Kinetic, the surfaces slide. They don't have time to settle down to have as great of interaction as you have when the surfaces are at rest, when you have the static coefficient of friction. It depends what the objects are. Rubber on concrete is a large value of static friction in comparison to smoother things such as wood on snow and ice on ice. These are examples of dry friction, with objects aren't lubricated, solid surfaces interacting. The two types are static and kinetic. And rolling is our third type. We'll talk about lubricated, smoother surfaces and fluids and drag friction later. When an object is falling, such as falling through a fluid of air, the air friction, the air resistance, is a force of air on leaves, on parachutes, on anything that falls through the fluid of the air, which we call a drag, but it's simply another force of falling through air. D stands for drag. It's the force of the air on the leaf, or whatever it is falling through the air. It's still force of 1 on 2, air on leaf. Drag is not a special type of force, just as friction is not a special type of force, just as the normal is not a special type of force. It's simply a force in the normal direction, perpendicular to a surface. It's still an object, air, interacting with another object, in this case the leaf. Friction, air resistance, and friction from fluids in general, air and water, are much more complicated than the static and kinetic and rolling frictions. It depends on the speed. As the object's falling through the air faster, the friction grows, and it depends on the square of the speed. The amount of air resistance depends on how much the object catches the air. So a parachute in our illustration is catching a large amount of air. The cross-sectional area of the parachute is interfering with the air. A smaller surface area has less push on the air than a larger surface area. So the drag, the air resistance, depends on the cross-sectional area. And if it's moving fast enough, it depends on the square of the speed. If it's slower, it depends on the speed. These are approximate equations. Answer this question on a blackboard. If a leaf falls or a car falls, which one has the greater air resistance? Don't confuse cause and effect, force and acceleration. Answer this question on a blackboard about an object, styrofoam ball, falling with some initial speed, but the resistance falling with initial speed, but the air resistance slows it down to what we call a final or terminal speed. And then it falls with a constant speed from there on at the terminal speed, which graph matches the description of the question. When discussing forces and force diagrams, if there is an imbalance in forces, a net force, forces don't cancel out, then net forces cause acceleration. Acceleration is the result of a net force divided by the mass. Once we have an acceleration, we can use our kinematic equations. If our net force is constant, we have a constant acceleration, and we can use our kinematic equations 2, 3, and 4 for constant acceleration. Here's a force diagram of an object such as a box being pulled by a rope. The box is on the ground, so its only contact force is the contact force from the rope and the ground. We break up the force of the ground into the force of the surface perpendicular, known as the normal force, and the force of the surface parallel, known as friction. If that is at rest, as we're told, box remaining at rest, then that's a static friction. Earth pulling down on the object is the weight. The normal force, the force of the surface perpendicular, responds to the weight to balance out. So we have a balanced force diagram if the object remains at rest. This is an example of Newton's first law. If the mass is 10 kilograms, then mass times gravity is weight, the force of the Earth on the object. The weight, the force of gravity, is 10 kilograms times g, which is approximately 100 newtons, 10 times 10. Therefore, the normal force, the surface perpendicular response, is balancing out the weight, 100 newtons up, to match 100 newtons down. If the rope is pulling at 30 newtons and the object remains at rest, the friction must be 30 newtons. Considering this, if this is the maximum friction, what must be the coefficient of friction, mu subscript s? Use your formula to figure out what that must be. Again, the box is being pulled, but this time it's being dragged across the surface. So it's an example where kinetic friction is applied, the sliding friction as the box is sliding across the surface. If the normal force is 80 newtons, then the upwards force must balance the downwards force because vertically the object is at rest, and so the weight must be 80 newtons. If the weight is 80 newtons, then the mass is 80 newtons divided by g, which gives us 8 kilograms. The vertical forces cancel, the horizontal forces do not. 60 newtons to the right, 20 newtons to the left gives me a net force of 40 newtons to the right. If my net force is 40 newtons and my mass is 8 kilograms, the net force divided by mass is acceleration. 40 divided by 8, 5 meters per second is the gain in speed of this crate. We can then proceed to use our kinematic equations with constant acceleration if the problem asks to proceed further to find velocities and displacements. Again, an object, a crate, is being pulled by a rope across a surface. It's being dragged, so you have kinetic friction. But in this case, the rope is at an angle of 30 degrees from the horizontal. First, let's find the normal force, the surface perpendicular. Well, the weight of the object is 100 newtons, but the normal force is not 100 newtons because the rope is pulling up and pulling over. The rope pulling up means there's an upward force from the rope in addition to the normal force. The normal force plus the component of the rope pulling up adds up to the weight pulling down. These two forces upwards cancel the weight pulling down, so vertically the object stays at rest. The component of the rope pulling up is F rope sine 30. Sine 30 is 1/2 of the hypotenuse F rope, so it's 30 newtons pulling up from the rope. Therefore, the normal force must be 70 newtons, because 70 plus 30 cancels out the 100 newtons of weight pulled down. Is there a net force? Not vertically, but horizontally there's more force of the rope to the right than to the left. The force of the rope to the right is F rope cosine 30 degrees, which is a greater value than 20 newtons. So F rope cosine 30, that component in the x direction, or parallel, the component of the rope in the x direction or parallel to the surface, minus the kinetic friction, the 20 newtons to the left, gives us our net force. And again, our net force divided by our mass will give us our acceleration. Solve for the net force and the acceleration. With this information, you can also solve for the coefficient of kinetic friction, mu subscript k. Do so. Let's say a 75 kilogram skier starts on a 50-meter high slope, where the slope is 10 degrees from the horizontal. His skis are frictionless, and so he moves across the snow without any friction. What would his speed be at the bottom? Well, we know the force of the Earth, gravity, his weight, is pulling him down the slope. So the component of his weight parallel to the slope is weight sine theta. And that force in the skier is the component of the force of gravity parallel to the ski slope, W weight sine theta. Thus, the net force, which is always mass times acceleration, is equal to his weight, mg, times sine theta. The normal force is balanced out by the force of the Earth pulling opposite the normal force into the snow. The forces from the force of the Earth and the force of the snow cancel out except for the force of the earth pulling parallel to the snow, because the snow doesn't respond with any friction. So my net force is only parallel to the direction down the slope. Our masses in our equation, ma equals mg sine theta, cancel out. And so acceleration equals g sine theta. The distance of the ski slope is 50 meters divided by sine theta, the hypotenuse of our right triangle of our slope. So now we're back to a familiar type of problem. We know the distance, we have our formula for the acceleration, so we can find our final speed from a known distance and a known acceleration. We can use the kinematic equation, Vf squared equals twice the acceleration times the distance, to solve for the final speed. Do so.